So we've looked at a number of algorithms. We've seen that comparison-based algorithms tend to be in the n squared to n log n big O. And it turns out that when we rely on the comparison of items, the best we can do is n log n. So that is the lower bound for sorting. The question then remains whether we can do any better if we place some restrictions on our data, or if our data fits certain characteristics. And it turns out that we can do that. So we can sort in linear time if we have additional information about our data. For instance, we would want to know what is the range of the key values that are to be sorted, or what are the number of values that are to be sorted. And so this then makes these algorithms not general sorting algorithms, because you cannot take any case and supply it to these algorithms and have the guarantee that it will sort efficiently. So there are a number of linear time sorting algorithms. We will look at two of them just to introduce the concept, to become familiar with some of the restrictions that we must put on the data, and to see how these work. So we will begin by looking at counting sort, and then we will look at radix sort. Counting sort is used to sort a collection of basically small integers. And the way it works is it counts the number of occurrences of distinct keys and uses arithmetic on those keys on those counts, excuse me, to actually determine the final position of that value in the sorted array. Its running time is linear in the number of items and the maximum key value, and we'll see that that's an important parameter in counting sort. And it is only suitable in situations where the number of keys is not significantly larger than the number of items in the array. And as I go over the example, I will point out why that's the case. And then when we look at radix sort, we'll see that is an algorithm that can sidestep some of these issues. So here's the basic method. We will assume that our input is made up of positive integers less than or equal to some value m for max, and we will and that input is initially stored in an array called data. We will then allocate an array called count, having m plus 1 elements, and again, m is the maximum value in the data array. And these elements are sometimes referred to as buckets. We will initialize these to 0. We will then go through the data array, and for every value that we encounter, which we're calling AI here, we will increment the count array at the AI index. Okay, once all the input is read, we will then update the count array to hold the number of integers less than or equal to I at location count of I. We will then allocate an additional array. So at this point we have 3 arrays. We have an array called data, which was our initial array. We allocated an array called count, which was of the size of the maximum value in data plus 1. And now we're allocating an additional array, which is the same size as the data array. This array called temp is what will hold the sorted output, and then we can actually copy that output back into the data array to wrap up the algorithm. So when we make the copy as shown there, we will place into temp at that index, which is a little bit cosmic to read, but the example should clear that up. So the index will come from the count index -1, and count is indexed by data I, and that will make more sense as we go over the example. And then finally, we'll copy everything over, and that'll be the end of the sorting routine. Having described the algorithm via pseudocode, this is a more formal look at the algorithm in code, and so just some key aspects to look at. We see that that first for loop determines finds the largest number, okay, so that we can set m, and then add 1 to it. So you notice that here what they call largest is what we called in the other slide m, okay. So we're dynamically allocating. The reason we're dynamically allocating this array is that we don't know what's in the array until we look inside, okay? And at this point, this is the initialization of the count array that we just created, initializing everything to 0. So I'm going to make one big comment here, init to 0. And this is the first phase, which increments the counter at that location every time a particular value is seen. And this transforms it, this loop transforms it to having seen less than, the number seen less than or equal to that particular value. And I'll go over this in an example. This is what moves through the original data array. You notice that I is the index in this for loop, and it's being used directly on the data array. And I moves backward from n-1 all the way to 0. And so this is what moves through that array and secures the value here and uses that same value to index into the count array and eventually set a value in temp. And finally, this last loop copies everything from temp back to the original array. And that is manifest then when the function exits. That sorted array is manifest back in the calling code. Let's walk through an example of counting sort. So I've placed the pseudocode up there and have numbered the steps. The one thing that I have not done with the count array is to initialize everything to 0 so that I don't have to do as much erasing. But let's just begin. We're given a data array of size n, and that's this data here. And you'll notice a couple of things. First of all, the maximum value inside this table is 13, and we assign that to m. And that becomes important because we have to allocate a count array that's of size m+1, as mentioned up here. The other thing that you'll see is that I have a couple of digits that are in different colors, and that's because there are duplicates of these digits. So there's a 4 here at index 2 and a 4 at index 9, and there's a 7 at index 5 and 1 at index 8. And so I have labeled the later values, the repeated values in blue, so that I can demonstrate that this particular algorithm is stable. You'll recall that sort stability means that whatever the order of the data is for duplicate data in the original array, that order is retained in the sorted array. And so let's begin then by allocating an array of size count. So all we have at this point is our data array. We have to look through it, find the max value, and allocate an array of size count. An array named count that has m plus 1 elements, where m is the greatest value of the actual data items, not the indices, but the actual data items inside of the data array. Okay, so we end up with this array, and I want you to imagine that there are zeros all the way across here. Just bear with me. So assume there are zeros, and I'm going to now execute step 2, which is to run through the array and to update. I'm going to run through the data array, and every time I find a particular value, I'm going to increment that index in my count array. So we're doing phase 1 of the count array. Okay, so I go through and I see my 5, and so I put a 1 there, I add it to the 0. I see an 11, there's a 0 here, imaginary, I add 1 to it. I see a 4, and I add 1 to it. And I see a 2, and I add 1 at index 2. I see an 8, and increment that by 1. I see a 7, I increment that by 1. I see a 13, increment that. A 10, increment that by 1. And now I see another 7. That means I have to increment this particular value, and that is now a 2. And then I see another 4, and so I have to bump up this count, and that is now a 2. And now I'm going to fill in these zeros that you've graciously allowed me to not have to erase these other values to put zeros. So everywhere where I didn't increment, there's a 0 there. It was there from the beginning. And I've now completed both step 1 here and step 2. Now we will do phase 2, which is again done on the count array. So this is 2 pictures of the same array. There aren't 2 arrays here. Basically, what I'm going to be doing now is I'm going to be transforming this from I've seen this many 2s, this many 4s, etc., to I've seen this many less than or equal to the index. Okay, this many less than or equal to the index. And so the way I do that is by running through the array again. So you notice I'm going from 1 to m, and I'm just saying that count of I plus equals count of I minus 1. So that's the same thing as saying count of I equals count of I plus count of I minus 1. So let's begin here. So I will begin here at index 1, and the value count of I is 0, and count of I minus 1 is 0. Okay, so there's already a 0 here. I'm just starting here, right, because it's the same array. And then I go to the 2, and you notice that count of 2 is 1, and I'm going to add this count that I just updated. And so what this means is I've seen one value less than or equal to 2. Where is that value? It's this one right here at index 3. Okay, the count of 3 is adding this count, what's in here right now, because this is the same array, to the previous value, and so that's a 1. Okay, the count of 4 is this 2 plus this 1, so it's 3. That means I've seen 3 things less than or equal to 4. What are they? This 2, that 4, and this other 4. Okay, and let's look at 5. That's going to be what's in here right now, which is the 1 plus this 3, so that's 4. The 0 plus this 4, so that is 4. And the 2 plus this 4, I've seen 6 things less than or equal to 7. And I've seen 7 things. Again, how did I get that? I took this 1 that was already in this box and I added to this 6. Okay, and then here it's the 0 plus the 7, so that's a 7. And here's a 1 plus the 7, so that's an 8. And here's a 1 plus the 8, so that's a 9. A 0 plus the 9, which is 9. And then finally a 1 plus the 9, which is 10. And a good cross check here is there happens to be 10 numbers up here. The maximum is 13. So that means that at index 13, I should have seen all 10 numbers, and that works out. And so we have done now phase 2. Okay, notice that we no longer have this array. This array has been overwritten below. Okay, so this is now our count array, and we're now going to begin positioning items. So we're going to go through the original data array. So these indices are for the data array. We're going to go through the data array backward. So we start at n-1, we go down to 0, and we're going to make this sort of crazy update here. But let's just take a look at the first one. When I is 9, data I is 4. So let's put that in here. Data I is 4. Okay, and so I'm going to index count with 4. So you see that the 4 is inside the red brackets, and whatever value is there, I'm going to subtract 1. So I'm going to go to count 4, which is this one. I'm going to subtract 1 from the value that's in here. So this is the count array, index 4, look at the value and subtract 1. That value is 2. And what I will do is I will place the value that's at index 9 in index 2 in the temp array. So the temp array is going to be what holds the sorted data. So this is the blue 4. Okay, this is the blue 4, and that's in there. And then I have to execute this line, which says decrement that particular count. So I'm going to decrement this to a 2. Okay, now we can get moving. We'll go to index 8. We decrement. Okay, and we see that there's a 7 there. We access the count array. Look at location 7. Okay, we see that there's a 6. Subtract 1 from it. That's 5. And place the 7 blue here, because that's what is at index 8 at the top. And decrement that particular decrement this particular value down to a 5. Okay, let's do to the next one. So we decrement, and we're now looking at index sorry, I scratched out the wrong one. We're looking at index 7. The value inside data 7 is 10. I access the count array at location 10, and I see that there's an 8 here. I subtract 1 from the 8, that gives me 7, and I place the 10 here, and then I decrement. Okay, so I had 7, 10, I went here. Okay, so I decrement this to a 7. And we've done this one. Let's go to index 6. What's there is 13. Look at the counter array. Look at value 13. It has the value 10. Take away 1 from it and insert the 13 down here. Decrement this by 1. And we're done with this one. Go to index 5. There's a 7 there. This is the green 7. Take the 7 and index the count array. There's a 5 there. Subtract 1. That's a 4. So this is the 7 green. And decrement that, make it a 4. Okay, and we're done with this one. Let's go to index 4. We decrement to index 4. What's there? There's an 8. Okay, access the count array, location 8. There's a 7 there. Subtract 1. That gives me index 6. Add the value 8 here and decrement this, make it a 6. And we're done with this one. Decrement the index. We're down to index 3. What's the value? The value is 2. Index the count array at index 2. I get value 1. Subtract 1. That's a 0. Put the value 2 at location 0 and decrement that value. And we're done. Decrement the data index I to 2. Look at data 2, and that's value 4. Come to the count array, index into it with value 4. I get the value 2. Subtract 1, that's 1. And that's where the 4 green goes. So 4 green. And I also have to decrement this particular value now. So that value is now 1, and we're done. Okay, we look at index 1. It's got value 11. Look at our count array. Value 11, index 11 has value 9. Subtract 1. That gives me 8. So place it in the 8. Location 8. And decrement this particular value. And we're done with that one. Finally, look at index 0 and we see the value 5. Take 5 into the count array index. It has number 4. Subtract 1. That's 3. And so I place the 3 here and decrement this by 1. And at this point, we've done everything that we've needed to do. Let's look at our array, see if it's sorted. Well, we've got a 2, we've got 4, and we've got another 4, so that's certainly in order. And look, green, the green 4 shows up before the blue 4 back here, so we have stability. We then have 5, then 7, followed by the other 7. The first 7 is the green 7, so we retain the order in the original data. The second 7 is the blue 7. We then have 8, then 10, then 11, then 13. So what we have here is we're sorted and we're stable.